LCR series resonant circuit is also known as voltage resonant circuit, and we'll explain also here the reason why it is called voltage resonant circuit. For a LCR series circuit, let us assume VR, VL, VC are the respective potential drops across resistor, inductor, capacitors respectively. Then we can directly apply the Kirchhoff's voltage law to write that the sum of the potential drops across each of the components is equal to the EMF of the source. That is E equal to VR plus VL plus VC, which we can write that E equal to IR plus L di by dt plus Q by C, which we can say equation 1. Now if you say the current here is I equal to I0 sin omega t, then we can write di by dt which equal to I0 omega cos omega t, and Q we can find by integrating I dt to be equal to minus I0 by omega cos omega t. If you substitute the value of I, Q and di by dt in the EMF equations as we have said here 1, then our equation will be equal to E must be equal to R times I0 sin omega t plus L I0 omega cos omega t minus I0 upon omega c times cos omega t. And if our I equal to I0 sin omega t, then obviously the EMF will either lag or it will be ahead, as in case of capacitor and inductor respectively. So we can write that EMF E which equal to E0 sin omega t plus theta, which is for, let us say, for inductor, and for capacitor it will be minus theta. So therefore E0 sin omega t plus or minus theta we will say, and that must be equal to I0 times in the right hand side R sin omega t plus within bracket omega L minus 1 upon omega c times cos omega t. And we can open here the sin omega t plus or minus theta term with sin A minus B formula to write the left hand side, that is E0 times sin omega t cos theta plus or minus cos omega t sin theta, which equal to in the right hand side as such I0 R times sin omega t plus I0 times within bracket omega L minus 1 upon omega c times cos omega t. Now we can equate the corresponding coefficients of sin omega t and cos omega t in left and right hand side to write that is E0 cos theta equal to I0 times R, and plus or minus E0 sin theta must be equal to I0 times within bracket omega L minus 1 upon omega c, and which will give us by dividing tan theta equal to plus or minus within bracket omega L minus 1 upon omega c whole upon R. And if it is a inductive circuit, then it is plus, tan theta is plus and tan theta is minus for a capacitive circuit, and we can show it in a phasor diagrams also. Square and add these coefficients, then it will give us E0 square equal to I0 square times R square plus I0 square times within bracket omega L minus 1 upon omega c whole square, and that will give us I0 equal to E0 by mod of Z, where this mod of Z is the impedance, which we can write as square root of R square plus within bracket omega L minus 1 upon omega whole square. At resonance, what happened? The amplitude is maximum and impedance is minimum, that is impedance only equal to the resistance, since I, current and voltage are in phase. So therefore at resonance, if we say the resonance frequency to be equal to omega 0, then omega 0 minus L minus 1 upon omega 0 c must be equal to 0, and that will give us F0, which is the resonance frequency, that is equal to 1 upon 2 pi times square root of LC. And here obviously the cos theta, which is the power factor, is equal to 1, and inductive voltage and capacitive voltage are equal and opposite at resonance. Now from the graph, if we say carefully, that is inductive reactance XL is directly proportional to the frequency, and after resonant frequency, if you see, this inductive reactance dominates the circuit and hence impedance increases with the increase of frequency. But in case of a capacitive reactance XC, inversely proportional to frequency, and within the interval of 0 to resonant frequency, the capacitive reactance, it dominates the circuit, and Z decreases with the increase of frequency within this interval of 0 to resonant frequency. In other graph, you see that voltage drop across the capacitor increases with frequency from 0 to a point B1, slightly below resonant frequency, beyond which this voltage drop across the capacitor falls with further increase in frequency and becomes 0 at frequency infinity. And suddenly at frequency 0, capacitive reactance, that is 1 upon omega c equal to infinity, which means an open circuit corresponding to the value of the source voltage, that is Vc equal to E0. And the voltage drop across the inductor, if you see, it increases with frequency from the frequency 0 to a point A1, slightly above the resonant frequency. It is slightly above the resonant frequency, beyond which this voltage drop falls with a further increase in frequency and becomes equal to source voltage, that is VL equal to E0 at frequency infinity, which corresponds to again an open circuit. And certainly at frequency 0, if you see, XL, that is inductive reactance, is 0. On the other hand, if you see carefully, the current and voltage drop across the resistors both increases with the frequency within the interval of 0 to resonant frequency, beyond which both these current and voltage drop across the resistor falls together. The phase at resonant frequency omega equal to omega 0 point is a point of inflation. That means that below the resonant frequency, the phase is driven by the capacitive reactance and hence the current is ahead of EMF, but this phase difference decreases within the interval of 0 to resonant frequency. Slowly it decreases and becomes the phase equal to 0 at resonant point. There is a reversal at resonant point, there is a reversal of phase, and again the phase is now driven by the capacitive reactance XL. That is, after the resonant frequency, the current is now lagging behind the EMF. A confirmation to this extent of LCR series resonant is observable when bulb glows with maximum illuminations when adjusted for values of L and C connected to AC source, of course. With a DC source, of course, it will never glow. Now, LCR series resonance is also called as a voltage resonance because at resonant frequency, the voltage across the reactive component of the circuit becomes extremely high, up to dangerous level even, over the source voltage. That often causes breakdown of induction coil or even the capacitor insulations, which can be proved as follows. We can prove it. At resonance, what happens? Omega 0 L must be equal to 1 upon omega 0 C. We can replace that omega 0 with 1 upon square root of LC to write that omega 0 L must be equal to square root of L by C, and that can be written as ZC, which is the characteristics impedance. The potential drops across the inductor and the capacitors are same, so therefore we can write VL equal to VC, which is equal to I times ZC. And this current, what is the current? How we can write? That is the EMF by resistance, because only impedance component is there. So therefore we can rearrange it. We can write it VL by E must be equal to VC by E, which is equal to ZC by R. Now if ZC is greater than R, then VL and VC with the potential drops are greater than the EMF, that is the source potentials. We can check this with an example, that is LCR series with an AC EMF 140 volt with frequency 50 Hz, inductance 0.2025 Henry, capacitance 50 microfarad, resistance of 0.2 ohm. Then the potential drops across the inductor and capacitor is equal to 44,540 volt, which is 318 times more than the source voltage, that is 140 volts. So therefore here the voltage is magnified, and that is why it is called voltage resonance circuit. However, this property is not always useful, so therefore it is avoided, but it is useful in tuning time. For example, it is useful for radio receiver circuit during tuning, of course within the safe limit of the BL and VC, that means the inductive and capacitive drops within that safe limit, to get AC voltage of greater magnitude than source voltage. When we tune, the tuning of receivers is objective is that to get AC voltage of greater magnitude than the source voltage. At that tuning time, it is also useful. Now coming to power dissipation, if you see, there is always interchange of energy between L and C. That is, in each half cycle of the current flow, the L and C stores equal amount of energy. And from figure we can see that as the current rises, the voltage drops in course of the first quarter cycle, the magnetic energy of the inductor increases and the electric energy of the capacitor decreases at the same rate. If you see, as we have taken I equal to I0 sin omega t, so we can take equal to E0 sin omega t minus theta, let us say. So here current is I0 equal to E0 upon square root of R square plus within bracket omega L minus 1 upon omega C whole square. Now if you want to calculate the instantaneous power, must be equal to E times I, that is equal to I0 times sin omega t into E0 sin omega t minus theta. Now we can open the sin omega t minus theta using again the sin A minus B formula to write, that is power instantaneous must be equal to E0 I0 times sin omega t within bracket of sin omega t times cos theta minus cos omega t times sin theta. And the average value of the power, if you want to calculate, you have to take P average, which is equal to E0 I0 being constant taken outside. The average of the first term we can write as sin square omega t cos theta, and the second term we can write minus E0 I0 by 2 and average of sin 2 omega t sin theta. And here we have used the property sin 2 omega t is equal to 2 times sin omega t cos theta, and we have multiplied 2 and divided by 2. So therefore again if you see that the average of sin square omega t is half, but the average of sin 2 omega t over a complete cycle is 0. So second term complete vanishes, and therefore the first term will be there to give P average, which is equal to E0 I0 by 2 cos theta. That is the average power, and this average power exists due to in phase component of current only. That is due to existence of resistor for which the power factor cos theta is equal to 1. P average can be written as also equal to ERMS and IRMS times R by Z mod, where Z mod is the impedance of the circuit, can be written as square root of R square plus within bracket omega L minus 1 by omega C whole square, and cos theta is equal to R by Z mod, and sin theta is equal to within bracket omega L minus 1 upon omega C whole upon Z mod. So therefore we can write that is the average power, which is equal to IRMS square times R, which is similar to the power dissipation in the DC circuit. And this power consumed due to resistors only. There is no consumption of power due to the reactive components, as because the cos theta is equal to 1 for only resistors or pure resistive circuit and 0 for the reactive circuits, and that is why often we say the current through these reactive components as wattless current. But of course the current here is not 0, but it is not consuming any powers. L and C acts as a storehouse of energy, like similar to that of the case of mitochondria. These are the mitochondria of electrical circuits, that is L and C, to store the energy, and of course without absorbing any energy. And this power dissipation is equal to E0 I0 by 2 in the form of Joule's heat. And to minimize these power dissipations, we preferably keep the resistor R at a low value, as we have seen in the workout problems. Coming to quality factor and bandwidth of the LCR series, if you see at resonance, constant amount of energy is stored by inductors and capacitors. That is, when this capacitive voltage drop is equal to maximum, inductor current is minimum, and vice versa. Hence you can write half C V max square equal to half L I max squares. And recalling the voltage resonance property of the LCR circuit, we see that a resistor of LCR series circuit usually low compared to the values of L and C. Hence the potential drops across the inductor and resistor is considerably high compared to the source EMF. And therefore we write the quality factor, which is equal to the potential drop across the inductor or capacitor upon the potential drop across the resistor. So therefore Q is equal to VL divided by RI, that is equal to VL or VC by RI, which also can be written as 2 pi times maximum energy stored per cycle upon energy dissipated per cycles. That is equal to omega 0 L by R, which can also be written as 1 upon omega 0 times RC, and that can also be written as equal to 1 by R square root of L by C, and which we can also write from the graph, that is resonant frequency omega 0 upon omega 2 minus omega 1, and that is equal to F0 by F2 minus F1, which is equal to F0 by bandwidth. Here bandwidth is F2 minus F1, and that corresponds to omega 2 minus omega 1, and omega 1 omega 2 are called the cutoff frequencies, and omega 1 is the lower cutoff and omega 2 is the upper cutoff frequencies. Now if you see, this bandwidth or the quality factor, which is a measure of sharpness of resonance, is used in receiver circuit to adjust L and C or both to attain maximum current for selecting EMF of a particular frequency, and hence called selector or acceptor circuits. As we have seen, it is useful during tuning circuits. At lower half power point A, the net reactance is equal to 1 upon omega 1 C minus omega 1 L, and accordingly the impedance Z is equal to square root of R square plus 1 upon omega 1 C minus omega 1 L whole square, and at upper cutoff frequency B, the net reactance is equal to within bracket omega 2 L minus 1 upon omega 2 C, and accordingly the Z mod, the impedance, will be equal to square root of R square plus omega 1 omega 2 times L minus 1 upon omega 2 C. We will discuss more about these LCR circuits in our subsequent class. Thank you.